So in part one of our discussion about quasars, we talked about their various aspects of their observed aspects, things like the fact that they are extremely far away, and therefore they must be extremely luminous, and also they vary on very short periods, which means they have to be very small as far as, well, certainly in relation to galaxies, they would have to be very small. To give you an idea, by the way, of how how small a galaxy is compared to, say, the solar system. If you took a typical CD or DVD and said, well, this is the size of our solar system. If you shrunk down our solar system the size of a DVD, how big would our galaxy be? Well, the spherical part of our galaxy would be approximately the size of the Earth. So we're talking extremely tiny compared to galactic sizes. And that's the size that the active regions of quasars are, maybe a little bit larger, maybe an old-fashioned vinyl record, something like that. But basically, that's the emitting region of quasars. So they must be very large, very massive, because otherwise they would be blown apart by their incredible brightness, by their incredible luminosity. And so that all points to a supermassive black hole of over, say, 100 million solar masses. So that's what we think the quasar engine is. And quasars are all very, very far away. These really, really energetic supermassive black holes that are swallowing up to a solar mass or more of material per year are all very distant. So what this is saying, because when we look far into space, we're looking back in time, that means that we're really seeing back to the early parts of the universe. So the early universe was filled with these phenomena called quasars. Now, there are other active galaxies that share similar properties. Quasars galaxies were discovered, I think, also in the 1950s or 60s. And these are spiral galaxies with bright quasar-like cores. The cores aren't as bright as a typical quasar, but they are almost as bright as the other parts of the galaxy put together. And the cores fluctuate in brightness over short time scales, just like quasars do, implying a size of only a few AUs. And measurements indicate masses of around 100 million solar masses in the tiny cores of the Quasars galaxies, pointing again to supermassive black holes as the power source. So that's another phenomenon that seems to be tied directly to supermassive black holes. Double-lobe radio galaxies are another. We think, in fact, that double-lobe radio galaxies are just active galaxies, or active galactic nuclei, as they're called, that are spitting out lobes of gas, of hot gas, on either side at very, very, very high speeds. This, in fact, is a composite picture. The galaxy in the center is an elliptical galaxy taken in visible light. The large, elongated things here are radio lobes. They are large blobs of gas that have been ejected from this galaxy. They're hundreds of thousands of light years in length. And many of them are millions of megaparsecs in length. There are several of these that are actually the largest connected structures in the universe. What we think is happening is that the supermassive black hole in the center of this galaxy has a very active accretion disk, and in addition to swallowing large amounts of material that are falling into it, the pressures, it's a very, very complicated hydrodynamic phenomenon, but the tremendous pressures that are caused by material falling in this accretion disk actually shoots out part of that disk in opposite directions at nearly the speed of light, or a good fraction of the speed of light anyway. And these hot disks or hot lobes of gas that have magnetic fields embedded within them end up giving off radio waves that make them shine in radio light. And if you could see with radio eyes, you would actually see some of these things that look like giant glowing Q-tips in the sky. They would actually be large enough to see with the naked eye, be resolvable with the naked eye. Okay, so it's an eruption at the galaxy's center caused by the accretion disk falling into the black hole. It ejects opposite jets of ionized gas in other directions. And here's an artist's conception of what seems to be going on. And you'll see, and this is very interesting because I remember seeing these in graduate school, these artist conceptions of the objects, and then a few years later, maybe 10 years later, the Hubble Space Telescope zoomed in on one of these active galaxies and showed it to be almost identical to the to the theoretical supposition of what it was. Pretty amazing. So the question then becomes, do all or most galaxies start out like quasars and then evolve into active galaxies and settle down as normal, quiet galaxies like our own? That seems to be the case. It seems to be that almost all galaxies have supermassive black holes. After all, our Milky Way does. It's possible that in the early stages of its evolution, our Milky Way could have been a somewhat unspectacular quasar, because its black hole is only 4 million solar masses, not 100 million solar masses. But it seems as though the size of the black hole or the mass of the black hole is connected in some way, some evolutionary way, to the size of the galaxy, or the mass of the galaxy that is surrounding it. And that's very curious. It seems to be that there's now some ideas of how perhaps galaxies came to be because of the supermassive black holes swallowing material, and the radiation from those black holes, or the radiation from those quasars, inducing star formation in the surrounding gas, and perhaps, in essence, creating the galaxy that surrounds it. That's one of the leading theories for how galaxy formation may have happened. But it is still an unsolved problem where the supermassive black holes come from. They're much, much larger than a stellar mass black hole, and we really don't know what made these supermassive black holes in the first place. So there's still a lot to find out in astrophysics. Okay, so that's about all we're going to say. There's a lot of other details about quasars and active galaxies, but we will move on in the next section to cosmology and the history of the origin of the universe.